So today I want to be talking about machine learning as applied to high energy physics. So I myself am not an expert at high energy physics, but I've been seeing a lot of recent papers, like more and more, posing high energy physics as a machine learning problem. So I thought it'd be really useful to see this work by a bunch of folks. Like there's some at Fermi, some at MIT, some at Northwestern, some at UCSD, and we can kind of get a general sense for how these problems are defined, and then sort of figure out like just the minimal physics background that we need to actually fully understand this work. So this is the first paper. So I'm going to be just taking notes on my tablet here. So they're saying like, okay, machine learning is becoming extremely prevalent in the construction of events in accelerator-based neutrino experiments, and these are computationally intensive. The data volumes of such experiments are rapidly increasing, and the demand to process billions of neutrino events with many machine learning algorithms inferences creates a computing challenge. So we explore a computing model in which heterogeneous uh, computing with GPU coprocessors is made available with the right amount of computing for a given task. Oh, okay. So it's sort of like this on-demand compute infrastructure. And with our approach, services for optimized network inferences, we integrate GPU acceleration specifically for the proto-Dune reconstructions chain without disrupting the native computing workflow. And so we accelerate the most time-consuming tasks, track and particle shower hit identification by a factor of 17. And so this results in a factor of 2.7 reduction in the total processing time when compared with CPU only. So for this particular task, only one GPU is required for every 68 CPU threads, providing a cost-effective solution. All right, this is already a pretty interesting outline, I think. So I think what we need to do is, well, we need to sort of figure out. Okay, well, they're saying let's first off figure it out what proto-Dune is, and then we need to figure out track and power, so track and particle shower hit identification. And taken together, these two things give us a pretty good sense of what we need to do. What we need to do next year. Here, I think I can make myself a bit bigger. So let me do this. All right. Let me see if this looks okay on stream. Okay, excellent. So this gives us like I said, like an outline of the kinds of stuff I want to be looking at today. So let's just do some quick googling. Like first, like this is I'm doing something new. Let's see, accelerator based neutrino experiments. So let's see what we get. Okay, oh yeah, it's literally people at Fermi as well. Solve the mystery of neutrino oscillations. Looks cool. I mean, this is cool from an artistic standpoint. I don't know how useful this is quite yet. Is there a Wikipedia page about this? Oh yeah, this is interesting. So we have Stanford Research Lab, and okay, we have Fermi Lab here. They send each other some particles. Like they send it. Okay, they shoot out neutrinos. They shoot out protons, and then they detect them. Okay, this kind of makes sense. So let's see. So they're saying they're looking at let's see, proto-Dune SP. Holy shit! So many co-authors. So this I think is a big paper. Okay, well, it's wow. I don't think I've ever seen a paper with this many co-authors before, ever. So two full A4 pages of authors and 2 pages of affiliations. Okay, so I don't think it's going to be realistic to read this whole thing right now, at least, but let's just sort of get a sense. So it's a single phase FAR detector prototype, a Dune construction of the first Dune mass detector module. Okay. Okay, so maybe let's just like look back at if we look at this paper, I think the things they're looking at is track uh, particle shower head identification. So particle. Okay, so particle identification algorithms and calorimetric energy measurements. So pions and proton beams and energy range from about 1 to. Oh, this is interesting because so this is like not a like if you want to identify these like subatomic particles, like you can't just do something like atomic spectroscopy because that like works at an atom level. So to get to these lower level techniques, like it sounds like you just have like a couple of minutes to identify it, and it's like the IDs are a lot more complex. To study electromagnetic cascade processes per genome plan, trigger rate, beam time request. Okay, I guess we can always come back to this paper some other time. So maybe let me just put down some notes here for later. Sort of anything I'm going to look at later, I'm going to put here. Let's just keep going over the paper, right? So they're saying like here, like zoom in, scroll this. This. I think my PDF editor just crashed. Just give us a moment. Okay, excellent. So fundamental particle physics has pushed the boundaries of computing for decades. As detectors have become more sophisticated and granular, particle beams more intense, and data sets larger. So the biggest fundamental physics experiment in the world has been confronted with massive computing challenges. Okay. So it's like sort of like the typical what you would expect to see in any sort of machine learning paper. It's like the data volumes are insane, and so they call it the Deep Underground Neutrino Experiment. So that's the future flagship neutrino experiment based on the Fermi National Accelerator Lab. And so they'll conduct a rich program in neutrino and underground physics, including the determination of the neutrino mass hierarchy and measurements of CP violation in neutrino mixing using a long baseline detection and measurement of atmospheric and solar neutrinos, searches for supernova burst neutrinos and other neutrino bursts from astronomical sources. Okay, just so I don't sound very stupid here, let's just let's quickly double check what a neutrino is, because I don't want I don't want to just give like a Neil deGrasse Tyson like explanation. So it's an elementary particle with spin of half that interacts only via the weak atomic subforce and gravity. So it's named because it is electrically neutral and because rest mass is so small that it was long thought to be zero. Oh, interesting. So the mass of the neutrino is much smaller than that of other known elementary particles. Oh, interesting. So that's kind of cool actually. So neutrino mass is not zero but very close. So it's difficult to measure exactly. Via proton, okay. Neutrino mass hierarchy. What's the neutrino mass hierarchy? Neutrino mass hierarchy. Oh, I see. And then neutrinos themselves have a hierarchy. Yeah, so like the different types of neutrinos, it's not obvious how much they weigh either. CP violation. CP violation. Or charge conjugation parity symmetry. Okay, so this is becoming sort of out there at this point. Like, okay, we're getting into like this whole dark matter stuff and how much of it really exists. But I would imagine, what this is trying to say, like, it's sort of trying to get to the question of like, why is there so much dark matter in the first place, or does it exist? Seem to be the two questions. Yeah, these are like Feynman diagrams. These are pretty cool. It shows you like sort of like you see these in category theory as well. All right, so the detectors will consist of 4 modules, of which at least 3 are planned to be 10 kilotons liquid argon time projection chambers. And so charged particles from neutrinos or other particles in fraction will travel through and ionize the argon. Okay. With ionization, electrons drifted over many meters in a strong electric field and detected on planes of sensing wires lends itself to applications of machine learning. So the result is essentially a high definition image of a neutrino interaction, which naturally lends itself to applications of machine learning designed for image classification, object detection, and image segmentation. So ML can also aid in other important applications like noise reduction and anomaly or region of interest detection. Oh, interesting. Let's see. So produced from neutrino other will travel through and ionize the argon with ionization electrons drifted over many meters in a strong electric field and detected on planes of sensing wires or circuit board charged collectors. Okay, so it sounds like to me, so this, like they're saying it's an image, but to me this sort of feels like it could be a graph or an image. That said, the funny thing about GNNs is that they use similar terminology to images. Like they also call it a convolution. It's just like the spatial locality is not determined by pixel space; it's determined in a graph space. All right. So, due to the number of challenge and long readout times of the detectors, the data volume produced by detectors will be very large. So, uncompressed continuous readout of a single module will be nearly 1.5 petabytes per second. Wow. And because most of it will not contain interactions of interest, a real-time data selection scheme must be employed to identify data containing neutrino interactions, with a limit on total bandwidth for all Dune modules, with accompanying compression. Oh, interesting. So, basically interesting, I see. So you need like what they're saying, I think, is you need a real-time detector to store data. It's an important point. So in addition to applications in real-time data selection, accelerated ML inference that can scale to process billions of data volumes will be important for offline reconstruction and selection of neutrino interactions. So the individual events are expected to have an order of the size of a few gigabytes, and extended readout events may be significantly larger. So it will be a challenge to analyze that data without an evolution of the computing modules that handle. Okay, moreover, some exists for a wide range of neutrino tricks, such as microbone. Okay, sure. So in this paper, they focus on the acceleration of deep ML modules as a solution for processing large amounts of data in the proto-Dune single-phase apparatus. So reconstruction workflow. For proto-Dune, ML inference is the most computationally intensive part of the full processing chain and is run repeatedly on hundreds of millions of events. So a growing trend is to improve computing power has been development of hardware that is dedicated for accelerating certain kinds of tasks, pairs with the GPU, natural parallelization, and ML algorithm, particularly DPR as a driver for computing artificial revolution. Okay, so what they're basically saying, I mean, this is still a bit high level. I would imagine they're gonna have more detail later. But what they're saying here is like, we need the compute, like, we need new architectures, GPUs work fine. So they want to deploy them as a service, which means that they just want to make it easy for other people that work at Fermi to just experiment with this data. Okay, then, so they're going to talk about, okay, so this is sort of the summary of the paper. So they discuss ProtoJune, they discuss how GPUs help, and how they integrate it within their framework. And then they're going to talk about like sort of the latency throughput measurements that they get. But this is sort of like an area you can kind of already tell that latency is crucial here, because like if you have something that's working in real time to figure out what you need to store, well, it better run really fast, because if it doesn't, then it's not particularly useful. So inference as a service was first employed for particle physics in 10. So the initial study utilized a custom field programmable arrays, oh interesting, by Intel Altera and provided through Microsoft Brainwave platform. Oh, interesting. I have a couple of friends at GraphCore that used to work at Altera. So these FPGAs achieved low latency, high throughput inference for large convolutional neural networks, such as ResNet. And this acceleration of event processing was demonstrated for the compact Moon-1 solenoid experiment at the Large Hadron Collider. Oh, interesting. Like ResNet was sort of the pioneer. That's interesting. So our study with GPUs for inference focuses on large batch size inference. So GPUs are used in almost simulation. All right. So modern ML algorithms have been embraced by the Neutrino reconstruction community because popular computer vision image processing techniques are highly compatible with the Neutrino reconstruction task and the detectors that collect the data. So they've applied a custom convolutional network inspired by Google Lunet to the classification of neutrino interactions for their segmented scintillator-based detector. Microboon uses a LARC detector, has conducted an extensive study of various CNN architectures and demonstrated their effectiveness in classifying and localizing single particles in a single plane. In addition, Microboon has applied a class of CNNs known as semantic segmentation networks to 2D images to classify each pixel as being associated with an electromagnetic particle. Dune, which will use also large peak detectors, and implemented the CNN based on SE ResNet. Classify neutrino interactions on simulated Dune far detector events. So lastly, recent effort. Okay, yeah, I mean, this is all about, so I would say, like, in general, like, you basically have a choice of detector and CNN architecture. So these are sort of the two things that sort of differentiate all this past work. So they focused on a specific computing workflow, the ProtoJune reconstruction chain, to demonstrate the power and flexibility of the sonic approach. So assembled and tested at the CERN Neutrino platform is designed to act as a test bed and full-scale prototype for the elements of the first far detector module of Dune. So it is currently the largest LARC ever constructed and is vital to develop technology required for Dune. This includes the reconstruction algorithms that will extract physics objects from the data, as well as the associated computing workflows. Okay, so I guess now we're finally going to describe the workflow. So it's the full offline reconstruction chain for the ProtoJune SP detector. So in each event, ionizing particles pass through the liquid argon, emitting scintillation lights that is recorded by photoelectors detectors. So the corresponding pulses are reconstructed as optical hits. And so these hits are grouped into flashes from which various parameters are determined, including time of a variable. Okay, so let's just have a sort of bullet point summary. So one is detection. right? 2 is some form of clustering. And then 3, so after the initial reconstruction phase, the web proceeds, wire hits, blah, 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 are then used to find, reconstruct wire hits, providing information such as time and collected charge. So once the wire hits have been reconstructed, the 2D information provided by the hits in each plane is combined with that from other planes in order to reconstruct 3D space points. So this information is primarily used to resolve ambiguities caused by the induction wires in one plane wrapping into another plane. Oh, I see. So it's sort of like, I would call this like a dedupe. Let me just put it here. So dedupe. And then this is clustering. And this is measuring. Which consists of a modular set provided by the finds the high-level objects, such as particles like tracks, showers, vertices, and assembles them into a hierarchy of parent-daughter nodes that ultimately point back to the candidate neutrino interaction. Okay, so this is the graph construction. So the final module in the chain is an ML algorithm that classifies reconstructed wire hits as being track-like or Michel electron-like. So this algorithm begins by reconstructing 44 pixel images. These images called patches are centered on the peak time and wire number of the reconstructed hit being classified. Oh, graph construction and then image creation. Interesting. Yeah, so it sounds like they're mostly going to talk about here. Like once, like this is all not ML. Like I would imagine this is all like heuristics that they've built up over, you know, like a long time. And so then the last step is like once you have these image patches, like you want to classify them. And then there's sort of the CNN is the last layer here. Right? So this makes a lot of sense now. Okay, so let's sort of look at what they're doing. So employed by ProtoDune 5x5 convolution using stride lengths, these feature mapped and fed into the dropout layers. The first branch terminates in 3 outputs and are constrained to a sum of by a softmax activation function, and the second branch terminates in a single output with a sigmoid activation function. Yeah, so this is you know, fairly typical. I mean, I'll just say typical actually. It's not fairly, it's just typical. So, okay, interesting. So ProtoDune, which provides common setup by many neutrino experiments that makes use of point ID, further particle physics application. Okay, we followed that is also in development, and with the coprocessor hardware used to accelerate the neural network is separate from the CPU client and accessed via a web service. Oh, interesting. Interesting. So just like client to server. So let's just look. I wonder if Larsoft is open source. Yeah, it is open source. Yeah, so I'll just have a quick note. So this is open source software. So, okay. So, okay, yeah, so they also, like, they're thinking, like, can we do, like, multi-threaded inference? So, let's just add this as a note. Yeah, so I'll say here, for example, they want to do inference with callbacks. The NVIDIA Triton Inference Server. What is that? Formerly, NVIDIA Tensor RT simplifies development of AI models at scale and production. And so it's an open source inference serving software that lets teams deploy AI models from any framework, from local storage or Google Cloud platform, to NVIDIA's data centers. I see. So how does this work exactly? Oh, okay. So, okay. So this is basically like NVIDIA Cloud. So they deploy 4 T4 and GPUs targeting data center acceleration. Per CPU with a direct connection over PCIe's, many worker nodes can send requests to a single GPU. Reduce dependency on open source in the experimental code base. Nice. Oh, interesting. Okay, so they basically have sort of like an API to plug in accelerators. So this is GoPress as a service. We will discuss future plans to demonstrate production full scale. So networking from client to server incurs additional latency, which leads to bottlenecks from limited bandwidth. So it handles loads balancing, multiple matters from various frameworks. There's dynamic batching, which combines multiple requests efficiently as task at hand. Oh, interesting. All right. So we performed tests on many combinations of computing hardware, provided a deeper understanding of networking limitations within both Google Cloud and on-premise data servers. So even though the tried-on inference server does not consume significant CPU power, the number of CPU cores provisioned for the node did have an impact on the maximum ingress bandwidth achieved by early tests. Oh, interesting. So client CPU, load balancer. Oh yeah, this photo makes a lot of sense. So to scale 4 NVIDIA GPUs flexibly, we deployed a Google Kubernetes engine for server-side workloads. Metrics on the overall health. Okay. Instead of describe machine learning performance, we describe the baseline CPU performance, we scale up the workflow and make detailed measurements. Let's just go to the numbers. Big batch clients, fraction percentage per job for different module categories. Server is handling inference requests from all CPU processes at the same time. Okay, I don't care about all of these details. Like, all I care about is what kind of speed ups did they see on GPU versus CPU. Because these details are a bit too much for what I'm interested in right now. Model small batch, model big batch, simultaneous jobs, processing time. Oh, I see. Model big batch, Trident. Number of simultaneous jobs, processing time. That's interesting. So One thing I don't quite understand here is why is it that the CPU only is a straight line? So we're basically saying that the number of jobs is constant regardless, but it's high. Yeah, let's go to the summary. It's accelerated by a factor, and total event processing time goes from on average in a factor of 2.7 overall processing time. To 1000, 2000 should be fairly straightforward. Be another interesting operational challenge. Okay, so this was still, you know, what's interesting is that this work is still a prototype. So it looks like they're using this to justify figuring out how much money they should be spending on GPUs overall. The total event processing time goes from 3 to... So what's M Mitchell track ID? So M track... Like reconstructed wires is being tracked like, shard like, or oh, I see. So I think this is like the image classification algorithm, really. That's what they're saying. Begins by constructing 48 by 48 pixel images, whose two dimensions are time. They're patches, and they're centered on the peak time. The value of each peak corresponds to the measured charge, the position, and the deconvoluted waveforms. Importantly, there are 48 to be classified. Typical event may have, because of the data is processed per wire plane, these are 55 pin batches of average size. Oh, wait a minute, so then... Oh, interesting. So it's many images with small batches. Okay, that's interesting, because like GPUs are particularly good for larger batches. So what they do is then they'll batch all of these like tiny images together. But I think this point is crucial. Like, let me see. Put this here. Images are 48 by 48 batches. Physics experiments would ultimately prefer to run the servers without relying on the cloud, instead using local servers in lab and conduct a single GPU server. Okay, sure. Okay, so things they want to try next, stuff like reduce precision. Next. Okay, so I think this was fairly straightforward. Like, so it sounds like, I mean, if you're really treating this as just sort of a pure machine learning algorithm, like all you're really doing is that you're working with many batches of image that are 48 by 48 in size, and if you can get a convolutional neural network to work really well in that domain, then you can build something that's very useful for these neutrino experiments. So I think that's enough. I think I may need to do like a separate stream to sort of really figure out how this stuff actually works. But I think like this is sort of sufficient, and we can actually just use this as a segue to go to the next paper. So next paper is similar. I think it's by the same authors too, if I'm not mistaken. So let's go here. Open. Then pinned folders, high energy physics. All right, very cool. So let's get started. So the demands in computing is going to continue to grow tremendously. CPU performance will be limited. We'll confront as the cloud is upgraded for high luminosity running. GPUs can resolve this couldn't be sufficiently accelerated to be large due to the adoption of deep learning algorithms, of GPU-based hardware acceleration for deep learning and the data construction workflow of high energy physics. Discuss strategy for the current seamless integration. Okay. Is this paper identical? Like, it's as if it's the same paper so far. It is different authors though, if I'm not mistaken. Let me double check. I have the paper printed out here. So Michael Wang, mine is different. Benjamin Hawks, Bert Holtzman. Yeah, there's Bert's is on both. Michael Wang on both. Doesn't look like it. Is Maria on both? Philip. Yeah, Philip's here. What about Benjamin? Okay, and then Tran's also here. Looks like he's the PI. Jeffrey Krupa. Yeah. It's a very similar authors. I mean, yeah, so I guess no surprise that this work is similar. So they have enormous data rates, so the challenges of processing this data can be one of the second tier of high-level trigger consists of CPU-based computing cluster on site at the Large Hadron Collider. High-level trigger CPU-based computing cluster on site at the third tier offline event processing consists of a globally distributed CPU-based computing grid. Okay, so they've so sort of this work is what they do is like the impact is discovering the Higgs boson or the nature of dark matter. So to contend with these strong dark matter constraints, physicists have been forced to rethink their approach to searching for dark matter and generically new physics models. This has led to development of light-dark matter models, predict signatures that could be produced but would be discarded in the early tiers of data reduction. So to enable the search for these particles, it is imperative to improve the quality of data reconstruction at all tiers of processing. So additionally, over the next decade, the Large Hadron Collider will progressively increase the beam intensity, resulting in more data generated by the detectors. Alright, so turns out you can't, let's see, write this here, you can't throw out all the pre-processed data. Higher energy beams produce more data. Okay, and then it sounds like most of their existing infrastructure is in CPUs. Okay. Oh yeah, so this is like what I'm just gonna call the low level detector, electron. Why is it starting to comprise significant? Okay, so let's see. So the gains from using coprocessors can be substantial, with improvements in algorithmic latency exceeding multiple orders of magnitude. They've been going for heterogeneous compute from ASICs, FPGAs, GPUs, all deployed to solve specific tasks. However, high energy physics experiments have thus far undertaken only limited use of alternative processors within the HLT and offline cricket, common use of machine learning. So HP have historically relied on ML as a way to improve the overall quality of the data and to separate small signals from enormous backgrounds. So DL approaches have used both for ML techniques. Has been clicked up to okay. Yeah, so it looks like their past uses have been like I'm gonna type this here. So past use for ML. is anomaly detection for signals. Can I reduce my brush size? I'm just like pushing too thick. Okay. Low-level detector and electron photon reconstruction and quark and gluon identification. By offloading the computational burden of these algorithms to GPUs while making minimal changes to existing CPU-based workflows. So to achieve this, we work on step by exploring the as-a-service paradigm. Okay. Oh, interesting. So I think like here they're just showing like just how much more compute they're going to be using. What's charged particle reconstruction? Charged particle. All right, so here it's like again they're talking about this whole thing about like non-blocking calls. So I think it's like I mean there really is non-blocking calls. An event containing a Higgs boson decaying to a bottom antiquark pair can lead to roughly 100 particles. And so we can use the aggregate properties of these particles to infer the presence of a Higgs boson. So the variety of particles with different signatures in each detector that may be present in any given collision leads to a large number of different coprocessors. So parallelization of the reconstruction algorithm that creates particles is possible by splitting the reconstruction into separate geometric regions and reconstructing the individual particles within that region. So further parallelization is possible through the separate by compiling separate reconstruction algorithm to modules, but some fundamental tasks such as track and clustering detector heads to form particles are the most computationally intensive. So but the potential for parallelization has only partly been realized through standard CPU optimization such as auto-vectorization. So in this work, large-scale batching of the reconstructions at a algorithmic level is achieved through the use of deep learning algorithms on the GPU. Okay. To apply deep learning under this, typically written in C++. Okay. Task-based multi-threading. Okay, this looks like okay. So next like couple pages here. Yo, hey Cedar Prince, how's it going? Sorry, I just saw you in chat. Like so, today I'm kind of looking at high energy physics. So there's these recent papers that I saw by Fermi and a couple of other researchers at different universities, going over how you can use machine learning to accelerate like high energy physics. So I'm not a physicist. Like my knowledge is like super basic here. I'm just like basic scientist. But the way they formulate them, they like all the MLs they use is relatively straightforward. So I thought we just kind of go over it. So far the first paper, because you weren't here, I'll just cover it. Like the first paper I covered was one using convolutional neural networks to sort of figure out like particle interactions for neutrinos. But I think this paper is actually a lot more in depth. Like they're going over many more examples. So my voice is a bit soft. Let me erase it. Is now better? How about now? Okay, excellent. Yeah, sorry about that. So let's see. So the simplest algorithm that we study is called the fast calorimeter learning, FastCal. It's a deep neural network with 2,000 parameters. So it was trained on simulated collisions using generator level information to, 15 inputs about raw charge, deposit, geometry. All right. It consists of a batch normalization layers and dense layers with the rectified linear unit activation function. As a core component, good resolution is important for sensitive measurements, so we find that local and global objects reconstructed with FastCal have as good or better resolution compared to the nominal algorithm that does not use ML. So it offers significant improvement in computing performance when operated as a service by reducing the CPU time, physics and computational performance. Okay, interesting. So what's going on here? So they're saying, like, I'm just trying to figure out like how big are these things, right? Like the fast calorimeter learning. Just 2,000 parameters. This thing is tiny. So I remember when I was visiting CMU, I befriended a postdoc who was using light in order to perform computations. I thought it was crazy and amazing. Yeah, actually, if you're interested, I don't know if this is super related, but because this is all like subatomic stuff, like it's very complicated, but sort of I think it's a similar idea. If you look at spectroscopy, it makes sense more for stuff that's larger, like that's an atom or larger, because it's basically like a way like where you can look at something and then like look at the light that it generates and then figure out like what the actual element is. So it's sort of like an ID for like physical objects, like or a hash key for physical objects, which I thought was kind of insane when I first heard about it. Like I first came across it like in the proteins area, but I'm slowly wanting to learn more about particle physics for work, and so we'll just see how it goes. Like, I feel like some of the problems overlap, or maybe not. We'll see. Okay, wait. So we said, oh, let's look at the FASL algorithm. Constraint programming. No, that's not what I want. "15 inputs, 2,000 parameters." Yeah, so tiny model. Wait, let me do this. So this is in general, yeah, like I think this was using some other ones, but there's like, I don't know if you've looked at this, but this is, because like when I first saw this, like my mind was blown. Like, check this out. It's like you'd think that there's one type of spectroscopy, but there's all these kinds. It's like, yeah, I think Raman is here. Oh yeah, this is used for chemistry, it looks like. So I think I've seen another one. It was the crystallography one was for protein. Anyway, this is it's a whole other topic, but yeah, I mean, like these techniques are amazing. Honestly, like I mean, it's like people have been doing some really hardcore math like way before deep learning became relevant. So yeah, but this is like a tiny model uh, with some dense layers and batch norm. For sensitive measurements such as events in Higgs boson, offers, okay. So it's electron regression. So Deep Galo is a mid-sized convolutional network trained for electron energy regression in the Atlas vector. Quite facile, energy from an entire region. Tiny images. Teeny tiny images. What happened to my shortcuts? I can't write like this is like watercolor. So I did some material science research with Raman specs, so I was curious how they got a unique hash key of an object, as you mentioned earlier. So I think like the video I felt explained it very well, like the one I linked. Like basically the main idea is that there's sort of a spectrum of light that each substance emits, or if you shine at it, it's like it either it emits it or it filters it out, and that apparently is a unique property of different elements, which I thought was insane. The technique they cover in the video is mostly for gases, but I think there's other techniques that work well for solids or liquids or whatever. Okay, so top corking, it's a ResNet 50, 21 3 million parameters, 49 convolutional networks, 1,000 class probabilities for natural images. Okay, so all of these are absolutely tiny. So I think like the sort of common theme I'm seeing here is this, and then can I write here? Or I had my nice shortcuts here. Where'd they go? Oh, it's okay. Oh, thanks, Cedar Prince. Appreciate you stopping by. To other major tasks in LHC computing, such as tracking. So specifications and GPU utilization of these three algorithms are summarized here. So trainable parameters. Okay, GPU memory usage. Where's that? 50. Okay, this is a good slide. Okay, so here then they talk about being able to perform stuff simultaneously. Scaling. All right, I think this makes sense. So basically, I think what I learned today was, let me just summarize it here in a couple of bullet points. All right, so maybe I'll just write it here. So basically, sort of a summary. So basically CNNs to detect, to classify and detect objects in small patches of images, like, you know, at most 50 by 50, and then deploy as a service easily for scientists that work at Fermi or the Large Hadron Collider. It needs to be non-blocking, heterogeneous compute. CNN is the first application, but others like GNN could replace earlier parts of the stack. So I think that's it. So I'm gonna just commit this. I'm gonna say LHS. Let's do this. So git add and then git commit -m high energy physics. And I think that's it for today. I hope you enjoyed it. I think this ended up being way more straightforward than I expected. So I'll probably I'm curious to now to see, for me at least, is what are how does this stuff actually work? If I did want to understand the basics of high energy physics, where would I start? And just use this as a starting point to actually start playing around with this stuff. I don't know how much of the data is actually open source and available, because if we're talking hundreds of petabytes, then this does seem like they can't even provide it to anyone even if they wanted to. So that's something we need to think more about carefully. So yeah, I hope you enjoyed it as much as I do. I'll see you soon. I think next installment will probably be about the ECS architecture. So if you're interested in how you can scale a game to millions of hundreds of thousands of entities on screen, it's sort of this really amazing design pattern that I think makes modern games possible. So I'll be going over examples of how it works in Unity, why the existing game object mechanism isn't like that. So if it's interested, be sure to check it out. Thank you so much, everyone.